Okay, thank you. Right. Hello, everyone. My name is Clemens. I'm presenting on smart contracts for Litecoin. So the content was prepared together with Laura, but I will do all the talking. So I want to give demystify all the smart contract business a little bit and give an overview over all the main classes of smart contract systems that could be deployed for Litecoin. So I'm not going to focus on the ones that currently exist. We want to look into the future of which kind of systems could be applied. So you can see the whole list on the left here. We'll walk through all of them in detail. And then we're going to compare all of them according to three properties. We're going to look at whether they can maintain the trustless nature of the underlying blockchain, because that's arguably the point of the whole crypto endeavor. We're going to look how expressive they are, which is a different word of saying can you express just like a single smart contract with these systems, or can you express multiple ones, or maybe even all smart contract systems. And then the last point talks about efficiency. So this, the way I'm formalizing it here, can you compute one value, who owns this token, without computing every single value? And that's important mostly in comparison to Ethereum, because the reason Ethereum is so expensive is because they're exactly not efficient according to this definition, right? So what we want to do here is we want to fill in this chart where you can see all the smart contract systems on the left and our three properties on the right. And so I already told you that Ethereum is obviously trustless, right? It's expressive, it can express all smart contract systems, but it is not efficient, right? And so I think this is actually the big opportunity where we could build something on top of Litecoin that's actually better than Ethereum and not worse, right? So let's just jump right in. So the most simple class of smart contracts that you could build for Bitcoin is just you have some just completely separate blockchain that interacts with the main chain in some way, right? So examples are stacks, the internet computer are built on BOP, right? And the way this interaction could work is, sometimes they can read and write, transactions from some smart contract on the L2 to the L1, and then sometimes the L1 asset is used in the consensus algorithm of the L2. So that's the case, for example, with stacks, right? And to use them, it's very simple. You go through an exchange, you buy yourself that L2 asset, and then you can use the L2. And when you want your L1 asset back, you just go back to the exchange and exchange it back. Second class is called sidechains. So these go back in time actually further than the interoperable change. So the main examples are Liquid and Rootstock on Bitcoin. And that is, again, a separate blockchain, but this time it's connected with the level 1 blockchain through what's called a two-way peg, right? And what this essentially just means is you take your Litecoin, you send it into the custody of some group of users called the Federation, right? And then once they've received your level 1 asset, they will mint you some tokens on the L2, right? You can then take advantage of the functionality of the L2, so maybe more throughput, lower fees, or sometimes smart contracts, right? And when you want your money back, your level 1 asset back, you send your L2 token back to the Federation. They burn with it or destroy it in some other way, and they will hopefully give you back your level 1 asset, right? The third class is called rollups, and those are the ones that have gotten a lot of attention lately, mostly through BitVM, because it was previously thought that this would not be possible on Bitcoin. So let me tell you how they work. So you can think of rollups as pretty much like a sidechain. It's just that this federation, this group of users that holds custody of your funds, is replaced by a smart contract. And also there's kind of no separate blockchain. So all the data for the L2 transactions are stored inside the level 1 blockchain, right? So if you want to use one of these systems, so what you would do is you would deposit your level 1 asset into the smart contract on the layer 1, right? And then if you want to use the L2, there's, since there's no separate blockchain, there's no, mining network that you can send your transaction to. There's some group of distinguished users called aggregators, and you would send your level 2 transaction to one of these aggregators, right? And the aggregator will then periodically batch together a bunch of these L2 transactions, compute the new state, and then they would publish a compressed version of all of this batch of L2 transactions together with the hash of the new state that has been computed by all these transactions would be published back to the layer 1 system, right? And then in practice, the way this works is there's usually, they haven't really been deployed on Bitcoin or Litecoin yet, but we can kind of look into what could be possible in the future by looking how these systems work on Ethereum. And so the big examples here are Optimism and Arbitrum, and in both of these cases, there's actually only one aggregator, right? So these systems are much more comparable to some cloud computing environment. where you just like, send some update request to the cloud computing provider called aggregator. They will evaluate it for you, post a new state root, right? And then, but what's kind of now different compared to cloud computing is that we do have the smart contract in place that sort of guarantees that the evaluation is valid, right? And there's two basic ways to do it, and we'll look at that on the next slide. But sort of just to wrap up the basic usage here is, what you would do is you would send a withdrawal request to this aggregator, and then they will sort of hopefully give you your level 1 asset back. So let's dive into this point of the ways that these smart contracts on the L1 can guarantee that the evaluation that the aggregator did was valid. And sort of there's two main classes called optimistic rollups and zero-knowledge rollups. In optimistic rollups, they're called optimistic because the basic assumption is that this aggregator sort of computes, the correct result, right? And sort of in this case, the aggregator would just like publish their transactions and the new state root to the layer 1 blockchain, and there's no validation whatsoever on the level 1 blockchain initially, right? And then there's some period of time in which other designated users called validators can submit what's called a fraud proof, which is just like a little proof that tells exactly, where did the aggregator kind of, compute the wrong result, right? And then these fraud proofs, again, so this fraud proof is then sort of submitted to the layer 1 smart contract, and the layer 1 smart contract needs to evaluate that. And if the fraud proof is correct, then the aggregator is fined. If the fraud proof is incorrect, then the validator that submitted the fraud proof sort of gets fined, right? And sort of if you hear these words fines in the crypto space, you can only take something, a real self-custodied asset you cannot take away from someone. So what happens is that both the validators and the aggregators need to sort of stake some amount of Bitcoin or whatever Litecoin, whatever the L1 asset is, so that if they behave badly, we can kind of take away from them, right? And that already tells us that this is much less peer-to-peer, than just level 1 transactions would be, because if you give someone the responsibility to handle, I don't know, $1 million, right? They have to stake at least $1 million to be fined, right? Because otherwise they just take the $1 million and lose their stake and still make money. So to be either an aggregator or a validator is really nothing that like individuals can do. This is all just a game kind of for big companies, right? So these are sort of the optimistic rollups, and second class is called zero-knowledge rollups. This is kind of the flip side, where sort of in optimistic rollups you assume that the aggregator doesn't lie, and validators have to prove otherwise. Here the assumption is that the aggregator sort of needs to prove every single time that they didn't lie, right? So what they publish is a validity proof, a proof that's evaluated by the level 1 smart contract to kind of show that they computed the correct result. And so these come in two different variants called snarks and starks. Starks are truly trustless, so this is great. So rollups with zero knowledge and starks are truly trustless, but they're very computationally intensive, right? Because they use this advanced cryptography called zero knowledge proofs that just require just like a ton of computation. So it's very expensive to evaluate a smart contract like that on a layer 1 chain like Bitcoin or Litecoin, right? And then the snarks are sort of computationally much less expensive. However, they have the disadvantage of not actually being trustless. They require some sort of trusted setup, just like sort of Zcash. Zcash uses snarks for their information hiding, all right? So, okay, so now we can start to fill in this chart, right? So we've seen that, like, sadly, none of these solutions are actually trustless to the extent that, Litecoin would be, right? So the interoperable blockchain, you have to go through some exchange. The exchanges are typically centralized and obviously regulated. You have to KYC, so you get, like, bad user experience and stuff like that. Side chains, you have to trust, you literally give your money into the custody of that federation, right? So that's very, very, like, not trustless, right? And then rollups, sort of, while in theory you could use these starks that are computational very intensive, I think in practice it's very unlikely that this will happen. And people, not even on Ethereum, where it's much easier to build these things in a trustless way, do people actually sort of use the systems that use these very, very compute intensive rollups. And so in practice, the ones that exist on Ethereum are not trustless, right? So that's kind of like a little bit sad picture. So the question is, if we want to get smart contracts on Bitcoin or Litecoin, do we have to throw away, like, essentially what makes Bitcoin or Litecoin, like, special, right? Which is the trustless nature. It's literally like line 2 of the white paper, right? And so to kind of take a more positive approach, you can kind of just see what people are actually using these smart contracts for, right? And so we have a lot of data on Ethereum that say that 80% of smart contracts on Ethereum are just tokens, right? So you can just like ask the question, what can Litecoin do, and what can we do natively on chain? So it's known that Bitcoin and Litecoin have had fungible and non-fungible tokens, since 2012 or something like that in the case of Bitcoin, like earlier than Ethereum even existed. So the question is, what can we do with sort of layer 1 smart contracts that don't use all this complicated tying together of two different blockchains, right? And so there's many examples now. So like I said, they go way back, in the Counterparty project and the Omni project go way back. It's been recently reinvented in systems called Ordnance and Runes. They have great properties, no extra blockchain, no trusted third party, just the metadata on chain. If you want to write smart contract to these kind of systems, you just broadcast a transaction with some extra metadata. And if you want to read the smart contract data, you kind of have some software that's specific to that protocol that will interpret this metadata and sort of spit out the smart contract data for you, like who owns which token. They come in two variants called block order based and UTXO based. Let me give you an example how this works. The block order based ones, what they do is sort of to write as usually just add metadata to transactions. To read and compute the state, you just each transaction in the blockchain one by one, right? And you just essentially interpret the metadata that's there, like an instruction to a computer, right? And then you use all these instructions to just build up one big data value, right? So you can see an example here on the right, where this is kind of like a simplified version of the BRC20 protocol. You can so it starts literally parsing the entire blockchain from the Coinbase transaction. When it finds the first BRC20 transaction, say it's a deployed transaction, and it's the metadata states that there is a new non-fungible token with the name Lite that's sort of now deployed and exists, and the max supply can be 1,000. Well, then the software would sort of just go ahead and update its internal value to reflect just that fact that you can see on the Lite there. Right, there's a token called Lite has a max supply of 1,000, right, and then keeps parsing, finds a second BRC20 transaction. This is a mint, right? Again, referring to the Lite token, where 100 of these Lite tokens get minted, and the software will just sort of update its internal representation, the value that it computes accordingly on the right. And now at the bottom in the box, you can see a transfer transaction that again references the token that's being transferred, and that one token is being transferred. And again, the software will update, kind of exactly, which owner owns how many tokens of the Lite token. Okay, so I mean that's pretty good, but we can already see this. So it's completely trustless and everything. But in terms of our criterion of being efficient and sort of being more efficient and better than Ethereum in a sense, we didn't make any progress, right? Because just like in Ethereum, we have to always sync a node to compute any single value. We're still going through the blockchain one by one and looking at every single transaction, right? So for example, client-side validation is just impossible in this world. So let's look at these layered. The second type called UTXO based is the ones that I like most. So again, to write data, you just broadcast a transaction with some metadata. But now we're computing, instead of computing one global value for all transactions together, we're doing something different. We're associating like one little value which each output of a transaction in sort of that's relevant to that protocol, right? And sort of the advantages are just like all the layer 1 solutions. They have self-custody. Okay, we'll see in a second that it's more efficient. Let's just look at these examples, right? So I've made examples for the Ordinals protocol and the Runes protocol. These are the ones that are like most popular right now for non-fungible and fungible tokens. So the way the Ordinals protocol works is it associates a natural number with every Satoshi ever mined, right? And then it associates a list of natural numbers with every output, right? And so if we see here this transaction at the top, the one that's labeled 1 through 15 billion, that's supposed to be the Coinbase transaction of the first block. The first block had 50 Bitcoin in it. That's 5 billion Satoshi. So the Ordinal software go ahead and associate that output with the list of numbers 1, 2, 3, 4, 5 up until 5 billion, right? And now the transaction you see below there that's sort of labeled 1 to 3 billion and 2 billion plus 1 to 5 billion. That's sort of assuming that this Coinbase transaction in the first block got spent by a transaction that has the first output 20 Bitcoin, the second output 30 Bitcoin. It'll sort of associate the two outputs with the sort of according series of numbers. Right, so it's just to give you a feeling for how these protocols work. Okay, on the right we can see the Runes example. Runes is a protocol for fungible tokens. So again, you just have some metadata that like specifies, okay, we're having a new fungible token minted here with the name Lite, right? And the terms are, you can mint this token 10 times. Every time you mint them, 100 tokens get allocated, right? And then you have a second transaction, the one that's labeled mint 1234. And what that specifies is sort of for the first time minting a token for the transaction that sits in block 123 and the fourth transaction in this block, right? And I'm assuming that this is kind of exactly the transaction that we saw there that reads Rune Light. And so the Rune software now can sort of understand that we're referring to minting that token. And since the terms specify that every time it's minted, 100 tokens gets sort of evaluated, the value associated with that output is, this output now contains 100 runes of Rune ID 123.4, right? And then in the transaction below, you can see how a token transfer is encoded in the Runes protocol. It's using a system called edicts that sort of specify that the first output would be associated with one token, and the second output would be associated with 99 tokens. Right? So this is now, the big advantage is now we don't have to go through these custodial complicated things that, require complicated setup and give a bad user experience. We have full self-custody. We're also much more efficient now. So we don't have to actually, if you wanted to determine the value associated with one of these outputs, you only have to look at, some previous transactions that can be reached through the inputs usually. And so you don't have to look at all of the transactions anymore. But you still have to look at a lot of transactions, right? However, the disadvantage of these protocols is that each of these protocols, and there's like I said, there's many of them. There's Counterparty and Omni and stuff like that. They're all special purpose. They only cover fungible tokens or non-fungible tokens or this kind of exchange. And none of these protocols are sort of composable in any way, right? So in Ethereum there was a popular protocol called 404. That's the simplest possible combination of a fungible and a non-fungible token. So it just adds a little piece of data to a fungible token. And you'd think you could combine the runes in your own sort of protocol to create, the 404 contract, but it's just impossible, right? So this is not a good way compared to Ethereum, where you can compose all these smart contracts in a nice way and build this beautiful ecosystem. These protocols just don't compose and are just sort of not expressive enough to capture all possible smart contracts, right? And this is where the Bitcoin computer comes in. There's the project that me and Laura have been working on for 5 years now. And so it's based on the exact same idea like the UTXO-based protocol before. It's just that we have our metadata format. Instead of inventing a new metadata format, we just use JavaScript, which is the most popular programming language that exists. And so the way it works is, like in the previous examples, we associate a value with every output of the relevant transactions. And the way it works is you can sort of inscribe a transaction with a JavaScript expression. The JavaScript expression can contain variables, right? And then you pretty much label your inputs with those variables that occur in your JavaScript expressions. And then the evaluator will sort of recursively look at sort of the output being spent, recursively compute that value there, and then sort of substitute that variable with that value, and just evaluate. Now you have sort of your expression with all the variables defined, and any off-the-shelf JavaScript evaluator can sort of evaluate it, and you can sort of compute new values here, right? So let me show you 2 examples. The non-fungible token, to create a new or deploy a new non-fungible token, you just deploy a Bitcoin transaction where the metadata is a very small JavaScript program that just completely explains what a non-fungible token is, right? So if you're not a programmer, won't make much sense, but if you are, you just have a constructor that just says, okay, it stores a piece of data, you pass some piece of data into the constructor to sort of create an object, and then you can transfer this object, you can pass in a public key and sort of specify the new user that way, right? And now, so that was the deployment of the, like in the previous examples, deploying the smart contract. Now, if you want to mint the first non-fungible token, you just call the constructor for that function, right? And it'll associate, that value with that output. Right? And now if you want to transfer that NFT, right, you broadcast a transaction that spends the output where the token was minted, and then sort of calls a function to sort of update the value, right? And sort of now on the right-hand side, you can see sort of an example for a fungible token, right? We're not going to walk through it. It's a little bit more complicated, but actually not that complicated. And it's also important to note that this is actually much simpler than the fungible token contract on Ethereum would be. Right? But then the principle is exactly the same. Again, if you want to mint a new fungible token, you call a constructor. If you want to update the state, you call a function, right? And you can sort of, this is a way that you can express all possible smart contracts. They compose very, very, very easily. If we wanted to build this 404 contract, that's kind of impossible to build with ordinals and runes. It's now just a very, very simple JavaScript program where just like into the constructor, you'd pass a little bit of extra data, and the software would just like compute it for you. So that's the Bitcoin computer. And so now we can sort of fill in our whole slide. Right? We can see that all these three lower rows here, they're called layer 1 protocols, right? And they're all completely trustless because they're just metadata on chain. You don't go through any custodians. You don't go through, trusted pegs, whatever. In terms of expressiveness, they're sort of for all the other existing ones other than the Bitcoin computer that I'm aware of, they're all special purpose, like I said, so they're not expressive according to our definitions, but the Bitcoin computer luckily is. And sort of the good news is that it is actually much more efficient than smart contracts on Ethereum are, because, like I said, in Ethereum you have to go through all of every single, you just have to sync a full node to compute any single value. You have to look at every single transaction. Whereas in the case of the Bitcoin computer protocol, as you can see here, if you want to compute the value of any of these outputs, you only have to actually look at as many transactions as the token had, updates pretty much, which is actually optimal. So if we build protocols like this, the hope is that we can actually, instead of building something that's kind of worse and more custodial than Ethereum actually is, we can try to build, show how Litecoin is amazing and actually better than Ethereum in some ways. And so to conclude, please come. So now for the first time since today, actually, you can. We've built these example applications. So we've built a block explorer. We've built a non-custodial wallet. They're all open source, all MIT licensed, and we've built an NFT trading site. So you can go to whatever nft.bitcoincomputer.io and try out these apps and see that they kind of actually work quite well in practice. And you can also scan the QR code there. We can kind of find the long version of this talk with like much more background information and also more information about the Bitcoin computer. Thank you very much. And now I'm ready to be made fun of. Thank you, Marty. All right. Thank you.
Good job.